So now we jump into the so-called environmental testing. And in fact, environmental testing, we can use the same idea, so that we have these highly accelerated environmental tests, which are, let's say, the purpose is the same as in halt testing. And sorry, few more acronyms. So now we have, instead of halt, we have HAST. So highly accelerated stress test instead of highly accelerated life test. The only difference here is that in halt testing we use temperature and vibration, but now in HAST testing we use temperature, humidity, and pressure. And pressure because we want to have high temperatures above the boiling point of water. I'm coming back to next week. We are discussing on these tests. There's the battle test. This is just one corrosion test. So here we include humidity and impurities, and also those are quite common, or most commonly they are the same point. Is we want to check how they withstand or how good our design is, how let's say our corrosion protection, how well it's made. Of course, this corrosion test can be also used to estimate lifetime. And let's see if Jonas is also joining next week and have a short introduction on related to these highly accelerated tests, maybe for hot and humid testing or corrosion testing or both. But anyway, if he is not joining, then I will have a few examples on those. And then we have, for the hot and humid conditions, we have these, let's say, not that highly accelerated testings, which are called typically temperature humidity bias tests, like 85-85 test. And this 85-85 is the, let's say, typical Finnish sauna test. So 85 degrees centigrade and 85 degrees relative humidity. So now let's, first we went to this direction, and now we start discussing about environmental tests. Let's first go through these tests, and then next Thursday we will go through these tests, so that we have and maybe even week after, within 1.5 weeks. So we still have 3 lectures, yes, left for the second part, concentrating on these tests. Okay, so first few generic things about the effect of moisture in general on the reliability before we go to the actual testing. And let's see if we have today time, we can also a little bit discuss on the effect of impurities in general. Okay, just checking that there's no questions. No, good. So now, as I said, how moisture typically affects on the reliability and why. And now my point here is more to make you understand that how this combined loading, where you have simultaneously moisture and something else, how the moisture, let's say, decreases the strength of the material against some other testing like temperature or mechanical strength. So that's the main point here now for the next few slides. And of course, as for example, we all know that ceramics or glasses, like our window, it is not affected by the rain in practice, because the water is not absorbing into the glass. So therefore, the properties of the glass stay the same. It doesn't matter how long you are keeping it outside. But now when we concentrate on the effects of moisture, most commonly we are talking about the effects of moisture on organic materials. And in electronics, of course, that means polymers. Naturally, when we have galvanic coupling, then moisture also can affect on the corrosion reliability. But even there, you need the impurities. I'm coming back to this issue later on. But just pure water typically does not cause corrosion, because you always need conductivity of the electrolyte. So therefore, let's first concentrate on the effects of just pure moisture and focus that one on the organic materials. Anyway, when we start disassembling our modern products, there are lots of polymers, organic materials there, which are sensitive to humid conditions. So first of all, we can say that if we are thinking about reliability, moisture almost always have negative effects on reliability. There are, let's say, I can recall only one specific failure mechanism, which is where, let's say, moisture is useful, and this is these electrical overstresses or static discharging, or so handling. When you have higher moisture content in the air, the charges which are, for example, float when you are walking or whatever, that's have more effect. So you will see it if you have not spent Finland yet the whole winter, and if we are going to get a decent winter in the Helsinki area next winter, you will see that in February, March, when the air is really, really dry, then you get these electrical discharges, these shocks much more easily than any other time of the year, because typically the moisture in the air kind of discharges this let's say the electricity which you accumulate yourself. So that would be the old, let's say, almost only. Maybe there are some more, but I cannot now recall any of the other failure mechanisms which would, let's say, benefit on high humidity. So yeah, the other thing is that if we are excluding the space, even avionics, we have always more or less humidity in the operational environments, and typically the amount of humidity is changing. As I said, it has, let's say, yearly cycles. Like in the summertime, you have more humidity, especially the absolute humidity is higher because you have higher temperatures. In the wintertime, you have lower humidity, especially lower absolute humidity. And then you have, let's say, changes in the humidity, for example, when it's raining or something like that, or even when the temperature is changing, because temperature and relative humidity, they are interlinked. So we will check that one in the next lecture, how the changes in the temperature also affect in the relative humidity, even the absolute humidity would stay the same. So you need to basically know that as in corrosion failures, also in humidity related failures, the first question is, do I need to do something? Because there are solutions in order to minimize the effects of moisture and impurities, but they always cost money. You typically need to add something, conformal coatings, like what we will discuss in the printed wiring boards, or some kind of a molding compounds or silicone gels or whatever, which slow down or prevent the diffusion of moisture and impurities. But if you don't need them, then why not to invest some money on this kind of a protection? So first of all, I think these are three important words here: condensation, adsorption, and absorption. So condensation, just we all know what condensation means. So it means that your surface is colder than the ambient. It means that the relative humidity at the surface is approaching the 100 degrees centigrade, so that the water which is in the air can condensate on the surface. And then when you have the water molecules at the surface, then they can either be absorbed or adsorbed. And adsorption now means that you only have the water molecules at the surface, which means that your surface insulation resistance is decreased, but it does not, in that sense, have any other effects, like it does not affect the mechanical strength of the product. It just decreases the electrical performance of the surface. So that can be, of course, very harmful, but it does not have this kind of long-term effects. And then when the water molecules really absorb, go inside the material, then you have electrical effects. So you lose the bulk insulation resistance, you lose the dielectric properties of your material, but you also affect on the mechanical properties of the material. And even these mechanical properties of the materials can be permanent, even the moisture goes away. And this is what mainly the next few slides are covering, this part. So why we need to be interested in the amount of humidity in our organic materials. So first of all our organic materials, they kind of have a loose structure. So if you think about what is, for example, epoxy, it's a polymer chains interlinked with each other, but there's quite a lot of empty space inside where the small water molecules can absorb. So it means that the water molecules can diffuse inside, and together with the flux water, there could be also some other elements like impurities, for example. There could be flux contaminants like what flux has, so soldering flux, alcohols, even the active components like chloride ions from the flux and so on. And when these water molecules are diffusing, absorbing inside the polymer, then it means that the bonds between the polymer chains, they are getting looser. It results swelling. So swelling is kind of a same thing that when you increase the temperature, the materials are expanding because of the coefficient of thermal expansion. But swelling is the same thing, changing the volume because of water is going in. And now these changes can be either temporary. So when moisture goes in, it is changing the properties, and then when water goes out, it is recovering back. But typically it's not like that. It's quite often permanent. So when these polymer chains are kind of loosened, then they are not coming back again. So it means that the material properties are permanently changed. I have a few examples coming in a few minutes. And then also these temporary changes. So when there is a lot of moisture inside the material, it affects on several critical parameters for our organic materials like glass transition temperature and thermal expansion. And as you know, if we are thinking about how these organic materials behave under thermal cycling or changing temperature, both these have a significant effect. And also this, let's say, moisture going in and going out, it causes similar type of let's say, changes as thermal cycling or creeping, so that the polymer chains, they are not recovering back. So you basically end up increasing the volume of the organic material, even the moisture is not anymore there. So important point. Maybe the most important point is this one, that when moisture goes inside your material, it decreases the glass transition temperature. So here is basically an example or two examples where you have, let's say, the strength of the material. So in this case, stiffness. Here, tensile strength. And then you have the glass transition temperature. Here also in the y-axis, and here it is stated here. And then you have in the x-axis, it's here temperature and here moisture content. So if we look first this one, so we have a dry material which is here, and we have a wet material which is here, and for the higher dry material, the glass transition temperature is higher. So we need to go on to higher temperatures before the polymer becomes in the, let's say, rubbery region instead of the glassy region. And how this is defined is that the stiffness, the strength of the material drops drastically. So now here it's strong, and here is less strong. And then when you increase the moisture content, so jump from here to here, you decrease the glass transition temperature, and your stiffness is decreased, but also the stiffness is decreased earlier when you go temperature up. Maybe this is even more, let's say, interesting example. This is from cyanide ester. Cyanide ester is one of the, let's say, high quality printed circuit board material. So if you want to have a very high performance, high reliability printed wiring board, motherboard, you purchase, instead of epoxy based, you purchase cyanide ester based, which is also one, if I recall correctly, is one type of epoxy, but cyanide ester has a different type of bond structure. Maybe some of you, if you have a background in polymer chemistry, you can explain a little bit better what is the basically difference there. But the point is that typical epoxy based printed circuit board materials, they have a glass transition temperature which is slightly above 100 degrees centigrade. Let's say the normal ones are 125, and then let's say high performance epoxies are from 150 to 175. So typically you try to pick it so that it's clearly above your operating temperatures, but it can be below your test temperatures. But now here in this case, there's the cyanide ester, which has, let's say, when it's dry, it has a glass transition temperature of 230 degrees centigrade, which is very, very high and good number. But then here in the x-axis, you see the moisture content. So even 0.2% moisture starts to decrease the glass transition temperature significantly. And when we reach 0.5%, then you have basically lost all the benefits for the cyanide ester in comparison to standard epoxy, because then your glass transition temperature have dropped down to 150. And simultaneously, here the open rectangles showing the tensile strength. It is first 15 megapascals, and then it has dropped down to something like less than 3 or less than 2 megapascals. So the strength has decreased. What is that in percentage? It's 80–90%. So these two diagrams, if you kind of remember the idea, it's really important. So you see how small amounts of moisture absorbed can drastically change the mechanical properties. And we know that some organic materials like epoxies can absorb much more than 0.5%. Even some references states that some organic materials which are used in electronics can absorb even up to 7–8%. Typically, we are talking about few percent. Epoxies, polyamides, which are the typical ones, they absorb few percent of water in weight maximum. And then the other thing which we need to consider is also how fast this absorption happens. So what is the diffusion rate of the moisture? So here I have another example. So these are all coming from this Suhir's, Ephraim Suhir's book, which is one of which I have mentioned from the course book, but of course you don't need to go on that book, but this is enough. So here we have underfills, epoxy-based underfill. So underfill is just a polymer which is put underneath a component, typically bare dye, and or between the bare die and the motherboard or printed wiring board. So when we talk about flip chip, I will come back on this. And if you have listened to Glenn's lectures in MMI, he already explained you let's say the point of flip chip and the underfills. So for now on, you just consider, okay, we have two polymers, epoxy-based polymers. So this is the time exposure time, and here in the y-axis we have the amount of water in weight percentage, and now the conditions are 85, 85. So 85 degrees centigrade, 85% relative humidity. So what does this mean? This means that there's no condensation. So nothing is condensating on the surface because the relative humidity is well below 100%. So the driving force is just the diffusion. You have water molecules, more water molecules in the ambient, and less water molecules in the polymer, and then there's a driving force for diffusing the water molecules there. And now what we can see is that this underfill B, it has smaller solubility of water and it saturates much faster. So now under these conditions, already after 50 hours, the maximum moisture content has been reached, which is roughly 1%. But on the other hand, for the other underfill, which is also an epoxy. So both are epoxies, but just with the different chemistries. So here we see that after 50 hours, this already has, let's say, 1.7 weight percent, almost a double amount of water, and it still continues to increase even after these 7 days. And in this Swiss book, they say that some epoxies can even continue absorbing water until several months. So 4,000 hours is close to 5 months, close to half a year. So it is really a process which takes time. So of course, these kind of things are now critical from the testing point of view. Okay, here we have a little bit lower temperature, which means that the diffusion rate is lower. But anyway, so again, when you're thinking about accelerating tests, so what do you use? Increase the relative humidity or increase the temperature or increase both in order to be realistic. Then another example here is how the moisture now, which is inside, affects on the mechanical properties of the actual polymer material itself. So now we have just to show that we need always to define how do we define the amount of water. So here in the upper picture we have the Young's modulus, elastic modulus as a function of moisture content in weight percent, and here is the same data, but the x-axis is concentration. So basically mass per volume. So of course these values are same, are different, absolute numerical values, but the effect is of course the same. So what we see here is that how the strength, the Young's modulus, I assume that you all recall what is Young's modulus, so basic strength curve and the slope of this elastic area. Or maybe I need to just very quickly try to draw it here so you have a like this. So this is stress, this is displacement, and typical. Okay, now this is, let's say, this elastic plastic curve is typical for metals. For polymers, it could be something like this. But anyway, here we have the yield strength, which means that up to here, when we increase the displacement, then everything is recoverable. So if we put stress, the displacement increases up to here, but if we release the stress, then the material comes back to the original position. So this area is elastic. And then, but if we increase the stress up to here, then this part here, we have permanent plastic changes, and then if we release the force or stress, then the material comes back like this, and we have a permanent strain here. So now we are talking about, when we talk about elastic modulus, we are talking about this slope. So the higher is the elastic modulus, the higher is the slope. So metals have high, and then polymers have low, or whatever. Ceramics would have even higher, like this. Okay, sorry about the confusing thing, but now at least everybody knows what elastic modulus is. So let's go back to the laser pointer. So this just shows that how the strength of the material is decreasing when the amount of water inside the polymer is increasing. And here, then again, exposure, 7 days, different conditions. So this is the control sample. So basically, just without any treatments. Then this shows if we put this epoxy-based polymer into 85 degrees, so only temperature. After 7 days, basically the strength has not decreased at all. Maybe a minor drop, but if you think about the error bars, there's no statistical difference. If you put it into 85 degrees and relatively low relative humidity, also not major change. But when you start increasing the relative humidity, then you see that with the same time, now here we have already 20% decrease in the strength if the conditions are 85 degrees centigrade and 95% relative humidity. So this example just shows how the moisture affects on the bulk strength of an epoxy. But that's not the only thing. It also affects on the adhesion between the epoxy and the metallization, which for us may be even more important. Because the epoxy in printed wiring modes, it's just a substrate. It does not have electrical functions in that sense, only that it is an insulating material. But we have the copper tracks there, we have the routing, and we want to be sure that the copper tracks also stay attached on the epoxy. And now the second example, which we still have 3 minutes time, is this is the strength of the interface between copper and epoxy. So now imagine that you have epoxy and then you have just copper attached to it. And now we are in the y-axis, we show what is the energy needed to detach this copper from the epoxy. So of course we want to have the adhesion as high as possible, and in the manufacturing there are several tricks what you do in order to get it. So this G here, is the interface or fracture toughness. So basically how many joules you need to fracture a certain area to detach it. And again, we have the same exposure time, 7 days. Control sample, new sample, only temperature, no major change. 85 degrees, 50% relative humidity, already significant decrease, and when you increase the relative humidity even more. And this corresponds to roughly 1 weight % of moisture content. Okay, that's one thing. When you put moisture in, you decrease the adhesion between copper and epoxy. But the other, maybe even more important thing is that if you compare the moisture saturated value, so immediately after the test, as well as recovery value. So here, what they have done is to, after the test, they put it on the furnace, get rid of the moisture. So basically, now if the material would recover, we should jump back to this value. But it's not recovery, only very, very minor thing. So what it means is that the interface strength is permanently decreased because of this moisture intake, even if you dry it. Okay, this is basically nice place to close our today's lecture. I will just show you what we have next. So now, in addition to moisture, then we start having different types of impurities. It can be even nutrient materials, meaning some organic contamination, which could cause, for example, fungus or mold growth. And then these, let's say, fungus can form corrosive organic acids, which then corrode your electronics. So your electronic boards could look like this. So next time we will start discussing what is happening if we combine the effects of moisture as well as the let's say the all different kinds of other impurities which are coming from the use environment, either organic ones or unorganic ones, so different, let's say, pollution or contaminants. Okay, so it is exactly 10 o'clock, so I will switch off the recording.